Hi everybody, welcome back to Viral Integrals. So today we're solving the classic integral with x to the fourth plus 1 in the denominator. The route is to compare it with a quadratic template we already know how to integrate. Here's the template we will use. On the half line, 1 over x squared plus a squared integrates to pi over 2a. We will use this as the bridge to the quadratic denominator. To see why the template is true, scale x by a. That turns the denominator into a squared times 1 plus u squared, and the remaining integral is the usual arctangent endpoint. Now look at the nearby denominator x squared plus I. If a squared is I, then this fits the quadratic template, so the next thing we need is the square root of I. Euler's formula is not introduced by name in AP Calculus, so we're going to build it from Taylor series. The series for e to the x, sine x, and cosine x are Calculus BC tools, and they are enough to get the formula. Plug I theta into the exponential series. The even powers of I become real, and the odd powers keep one factor of I. Now group the real terms and the imaginary terms. The real group is the cosine series, and the imaginary group is I times the sine series. This gives Euler's formula, quite possibly the most important formula in all of mathematics. E to the I theta equals cosine theta plus I sine theta. We learned it from Taylor series, so now we can use it in future videos. Use Euler's formula at theta equals pi over 2. Cosine pi over 2 is 0, and sine pi over 2 is 1. So e to the I pi over 2 equals I. We will use the principal square root. Since I equals e to the I pi over 2, its principal square root is e to the I pi over 4. Squaring e to the I pi over 4 gets us back to I to make it fit the template. So here's the formal leap. We are extending the quadratic template to the principal complex value a is equal to the square root of I. With that caveat named, x squared plus I becomes x squared plus square root of I squared. So the template gives pi over 2 square root of I. Now convert the result into real and imaginary parts. Euler's formula tells us what e to the negative I pi over 4 equals. Now rewrite the same integral by multiplying by its conjugate. That makes the denominator x to the fourth plus 1. Now split the numerator. The real part has x squared upstairs. The imaginary part is negative the integral we actually want. Compare the imaginary parts from the two versions of the same integral. The template result has imaginary part negative pi root 2 over 4, and the written integral has imaginary part negative I. The negatives match, so I equals pi root 2 over 4. That is the same as pi over 2 root 2, which is the final value of the original integral. So that's it, guys. The value of that integral is pi over 2 root 2. And displayed here on the screen are some results that we are going to be using in future videos. Again, I hope you enjoyed that, and we'll see you next time.